So what I want to do is I want to bring together that statement that we just said, and I want to write it right here on the side, that a series, I'm just going to write down what we just wrote on the board. A series is said to converge if its corresponding sequence of partial sums converges. And that means that if we look at the nth partial sum, and if we let that nth partial sum run n to infinity, if that thing exists, then we say that's the sum of the series, okay? So this is the mathematical theory behind what we're doing. So an infinite series is an infinite summation, and it's said to converge if its corresponding sequence of partial sums converges. So we are going to look at the sequence of partial sums, and we are going to look as n gets bigger and bigger and bigger. So as that number gets bigger and bigger and bigger, does this limit exist? And if it does, then that's said to be the sum. That's the theory behind what we're doing. But now let's put the math behind it. Suppose I asked you to write out S sub 4 if we're given that A sub n equals 4 to the n over 7 to the n plus 9 to the n. What would S sub 4 look like if I was writing it out? What would it be? So I'd have to take the first term when n is 1, right? And I would have to put 1 in for n. And that gives me my first term in this sum. Then I have to add to it, I'd have to add to it when n is 2, right? I'd have to add to it when n is 2. And so, John, can you help me? What would I get then if n is 2?
16.
Yep, I'd get 16 over 49 plus 81, right? That would be when n is 2. And then when n is 3, what would it be? It'd be 4 to the third, which is 64, right? Over 7 to the third, don't know what that is. Over 9 to the third, 49 times 7, and then 9, right? And n sub 4 is when I have 4 to the fourth over 7 to the fourth plus 9 to the fourth. Now we could sit down and calculate all those fractions out and add them up. But it's messy, right? It's so messy. And that's why we are going to use our calculators and Desmos to help us compute S sub 4, okay? So we want to compute S sub 4. To compute S sub 4 using Desmos, we're going to go over to Desmos. Okay, so I'm going to pause here. I'm going to go stopping.
Desmos only computes 512 terms or something.
Oh my
You
goodness.
can only take the 0th term to the 511th term.
Oh my gosh, that's so crazy. Wow. So we see that Desmos does have its limitations, huh? Calculators have their limitations, don't they? But we would say that the sum of this series is 0.4865374514515. And let me go back to what we were looking at. So we would say that S sub n, so if we looked at S sub n, and if we looked at the limit as n goes to infinity of those numbers, we got the same thing. because this started a pattern repeating. Now, of course, Desmos has limitations, right? This actually would have more digits at the back end, right? But this is where it's heading. It's heading to a number like this, and then other stuff at the end of it. But it's heading to a finite number. So we would say that this is the prediction for the sum of that series. We would say that if this limit exists, then that would mean that this infinite summation, if this limit exists, provided this limit exists, which it does, this would be the sum of the series, and we would say it's 0.486537 ... right? Okay. That's the terminology. So as a practice, do the same thing for a sub n equals 1 over 2n minus 1. A sub n equals 1 over 2n minus 1. On Desmos, does this thing appear to be converging and diverging? And if so, what is it converging to? And James, I think I'll use your quick trick now. Now that we have this visual for seeing what it does, I might do what you said. Oops, got to make sure. When you plug it in, guys, make sure that you put that n up there in the exponent, the n minus 1 up there in the exponent. You don't want to bring it down. Wait, why isn't it working? I messed that up. Something's not right. 1 divided by 2 raised to the n minus 1. Yes, like that. So the first one is 1.875, the second one is 1.9375, the third one is 1.998, the next one's 1.999, right? Is that what you guys are getting? And then 2, are you guys getting that it goes to 2? So it should go to 2. You see that? You got it? Okay, just check it. Just check it, making sure you got it.
Yeah, it converges to 2.
Yeah, good. Converges to 2. But do you guys see how to use Desmos to get that? Okay, so one way, and now we can close up. We're done with that for a little bit. So once you guys get that and you write that down in your notes, okay, you can close up your computers, all right? Because now we're going to talk theory. So I'll just write down that S sub 500 is 2. S sub 100 was 2. And so if we looked as n goes to infinity, we're predicting that as n goes to infinity, this summation goes to 2. So we are predicting that the series 1 over 2 to the n minus 1 converges, and it converges to the sum of 2. Okay, not all series converge. And we'll talk about that a little bit next time. But what I want to do now is introduce 2 specific types of series, okay? One's called a telescoping, and one's called a geometric series. So, in general, to find the sequence of partial sums and to see if it converges or diverges, you kind of need some technology, okay? But there are 2 special cases where you don't need technology, and you can decide if this sequence converges or diverges, or this series converges or diverges by looking at the partial sums. The first of them is called the telescoping series. So as a preface, I want to ask, have you guys seen Pirates of the Caribbean or a pirate movie? and the pirate captain wants to goes out on his deck, right? And he pulls out this device from his pocket, and he pulls it apart, right? And he expands it. What do we call that thing? What do you guys call that thing? Have you guys like a telescope, right? It's like a telescope. It's like a telescope, right? But it's one of those collapsible telescopes, right? Because the captain doesn't keep the whole entire telescope open. He puts it in his pocket, so he smushes it down, right? And when he smushes it down, it gives you a nice little, right? Like a telescope, it gives you this little compact thing. So the idea is a telescope, we want to look at something which expands out, but can also smush down into something nice and compact. You guys camp? I think some of you guys were Boy Scout. Is anybody Boy Scouts or Girl Scouts?
I'm not.
Was that the other class? The other class had some Eagle Scouts in it. But if you go camping, you ever have collapsible cups? Does everybody ever go camping with a collapsible cup? And so, right, because you want to store it, it's easier if it's flat versus big. Okay, so that's the idea with the telescoping series. We are going to expand out an nth partial sum, and then we want to collapse it. So with a telescoping sum, the whole goal is to look at the sequence of partial sums, take the limit as n goes to infinity, and decide if it converges or diverges and what it converges to. But we're going to build up to that, okay? We're going to build up to that. I want to start first by just computing the first partial sum. And what is that? That's just putting n equal 1 and writing down what that first term is, right? So if I put n equals 1 into my series, what are you guys getting? 3 plus 1. Well, I'll just write it in for us here. What did you get? 1 over the square root of 4 minus 1 over the square root of 7. Is that what you guys got? Or in other words, you got 1/2 plus 1 over minus 1 over the square root of 7. So we would say that's our first partial sum. Let's write out the second partial sum. So the second partial sum says, okay, well, let's start with that first term, a sub 1, but let's add to it a second term, a sub 2, or in other words, n equals 1 and then n equals 2. So I already did n equals 1, so I'm just going to rewrite it in here. But now I let n equal 2. And I have 1 over the square root of 3 times 2 plus 1 times 3 times 2 plus 4 minus 1 over the square root of 3 times 2 plus 4. Or in other words, I have this series 1 over minus 1/7 plus 1/7 minus 1/10. Well, that's kind of cool. Do you see that the square root of 1 over the square root of 7 cancels? Oh, that's kind of nice. Well, let me look at S sub 3 quick. S sub 3 is those first couple terms. Let me write them down again. And that's when n is 1, and then when n is 2, and then now we have to do when n is 3, right? And so I'm getting 3 times 3 plus 1. I think I'm getting 3 times 3 plus 1 minus 1 over 3 times 3 plus 4. I think I'm getting 1/2 minus 1 over the square root of 7 plus 1 over the square root of 7 minus 1 over the square root of 10 plus 1 over the square root of 10 minus 1 over the square root of 13. You guys see what's happening? So what is happening is that as we list out terms, we're noticing a pattern. We're noticing that things are starting to cancel for us. So let's go all the way down to S sub n, and let's write out S sub n. So it starts out with 1/2 and then minus 1 over the square root of 7. And then it goes 1 over the square root of 7 minus 1 over the square root of 10. And then it goes 1 over the square root of 10 minus 1 over the square root of 13. But S sub n takes me all the way back to the end. So let me write this out. This is my first term that I add. This is my second term. This is my third term. I want to get in the habit of writing out both my nth term and my n minus first term. And I'm telling you this for a reason, not because I'm trying to make you do extra work, but because I've taught this class for so long, I'm telling you, put both the n minus first term and the nth term in that summation. And show me what you get. Put the nth term and the n minus first term in. Just do it in one example. I know you can see it. I know you can see it. Like I said, I know that it's shortcut. I know we can see what our shortcut's supposed to be and where we're supposed to get to. But for our notes purposes, I want to put n minus 1 in, and then I want to put n in. So let me just see. So n minus 1 is going to give me 1 over the square root of 3 times n minus 1 plus 1 minus 1 over the square root of 3 times n minus 1 plus 4. And a sub n is going to give me 1 over the square root of 3n plus 1 minus 1 over the square root of 3n plus 4. So let me put those up. 1 over the square root of 3n plus 1 minus 1 over the square root of 3n plus 4, and the one before it. Ooh, if I combine this, did you guys get 3n minus 3 plus 1? Did you get 1 over the square root of 3n minus 2? And then 1 over the square root of 3n plus 1? Is that what you guys got for those two terms? I'm going to stop for a sec. Telescope it down. But when you telescope it down, be very careful. I want you to note a couple things. I want you to note positions. This is the first guy that cancels, happens to be minus 1 over the square root of 7. And that guy is going to cancel with plus 1 over the square root of 7. But what I want you to notice is how it cancels. It's the second term in a sub 1, and that cancels with the first term in the next one. Minus 1 over square root of 10 will cancel 1 over, right, with the next one. Do you see that? Minus 1 over square root 13 would cancel with something I haven't written down, right? And so forth goes the pattern. Now when I get to the back end, this term, which happens to be a first term, he actually is canceling with one before it, right? The first term cancels to the second term before it. So he's actually canceling right before it. And then this guy cancels with this guy. And so if we want to write out S sub n, we would say that's 1/2, the first term. Everything in the middle cancels, so we're going to smush it like a telescope, like a pirate ship telescope. We're going to smush it down, and this is going to be S sub n. And how do we tell if a sequence converges? We take the limit as n goes to infinity, and so we're just going to take the limit as n goes to infinity on this partial sum, the nth partial sum, and what happens as n goes to infinity? Andrew, what happens? It goes to what?
Approaches 1/2.
Yeah, because this part goes to 0. As n goes to infinity, that part goes to 0. So this sequence of partial sums goes to 1/2. And we would say then that this series, 1 over the square root of 3n plus 1 minus 1 over the square root of 3n plus 4, we would say that this series converges to 1/2. Does that make sense? Now your homeworks are a little trickier, but does everybody see what we did, right? So to get the nth partial sum, which you're going to be asked to do on your homework, you have to do a sub 1, a sub 2, a sub 3, and make sure you list the last two terms. Smush things together, and then write down what you're left with. And then take the limit as n goes to infinity. Any questions on this problem? So then we want to look at this guy right here. Let's consider this infinite summation. N equals 1 to infinity of 20 over n squared plus 6n plus 8. So, notice the key to having the last guy telescope was that we had our original series equal to a sum of two separate things, so they canceled each other, right? So our first goal right here is to take this rational expression, 20 over n squared plus 6n plus 8. So we want to take this guy here and rewrite it. And the first class couldn't remember this as well. It was a little rusty. What do we do? Go back to section 7.4, partial fractions, which we used on our first test. What do we do if we have a rational expression and we want to rewrite it as a sum of two smaller fractions, right? A sum of two smaller rational expressions. What's the first thing we do if we want to use partial fraction decomposition? What do we do first? Factor? Factor. Thank you. Thanks, Max. We absolutely want to factor. Somebody want to factor this for me?
N plus 2, n plus 4.
N plus 2, n plus 4. Because 4 times 2 is 8, and 4 plus 2 is 6. Beautiful. So our first step is factor. What's our next step if we want to rewrite this as partial fractions? What's next? Kayla?
You have to, substitute the top for A and B.
So we put a letter on top, didn't we? Do you guys remember doing this?
Yeah.
And then we put B on top. And then we combine those fractions, right? And set up a system of equations. I'm going to let you try that. I'm going to pause because this is good. We started by getting a common denominator. So like this guy would multiply by n plus 4. And the next one would multiply by n plus 2 over n plus 2. And we would put it together. And that would give us an plus 4a plus bn plus 2b all over n plus 2 times n plus 4. And then so there's different ways. Actually, some people don't multiply it out. Let me undo that a second. Some people started to not multiply it out, but some people did. So let me just write it out before we multiply it out. Some people wrote it like this and then put a -2 in and a 4 in and solved it, which is very perfect. But when we introduced it, I think we put our n terms together when we first introduced this, and we put our n terms together. And then we put our other terms together, and then we set up our system of equations. But again, I'm going to keep wandering. So there's no n in my original problem, so you could write down a plus b is 0, and then 4a plus 2b is 20, because that's the constant. And then you would solve this using substitution or elimination. I think I'm going to rewrite my original series myself. And then I like elimination method. It's just my thing. So I would probably multiply everything by a negative and add down. Are you guys getting some numbers for A and B then? I get A to be 10. And I get B to be negative 10.
Wait, how does that work in the equation though? If it's,
Yeah, let's see. So on top, what I did was I rewrote this as A over n plus 2 and B over n plus 4, right?
I mean in the 4a plus 2b is 20.
4A plus 2B is 20.
Oh yeah, that would be 40 minus 20.
Does that work?
Yeah, I just got stuck with it.
So really what that means is we're looking at this series. Let me get rid of some of these. Okay, so I'm going to erase this stuff here so that I have space. Okay. And so what I'm really doing is I am looking at the infinite summation n equals 1 to infinity of 10 over n plus 2 minus 10 over n plus 4. And now I'm good because remember, our goal is to do a telescoping series. And a telescoping series is that idea where you have these terms and they're going to cancel, and so everything's going to smush down, right? So the idea is we want to be able to smush them down and cancel a bunch of things. So I want you to find S sub n. So the directions are, now that we've used partial fractions to get my rational expression rewritten, now I want you to list out S sub n. And I'm going to tell you again, I want you to find A sub 1, A sub 2, A sub 3, and you might even want to find A sub 4 for this problem. And then I want you to go to the back end, and I want you to find those last couple. You might want to find A sub n minus 2, A sub n minus 1, A sub n. So find those terms and list them all out, string them all out, and show me what you're getting. I'm going to wander to make sure you can do this, because a lot of people last semester struggled with these problems on their homework, so I want to make sure everybody's on board. See some numbers like you. Yeah, things are interesting when you let n equal 1. So when n is 1, you get 10 over 3 minus 10 over 5. That's your first thing. And then when n is 2, you get 10 over 4 minus 10 over 6. And then when n is 3, you get 10 over 5 minus 10 over 7. And then 10 over 6 minus 10 over 8. Do you guys see a pattern, huh? I'm going to go n minus 2. So let's see, 10 over n minus 2 plus 2, and 10 over n minus 2 plus 4. So I'm getting 10 over n minus 10 over n plus 2. And this guy is 10 over n minus 1 plus 2, 10 over n minus 1 plus 4. So that's giving me 10 over n plus 1, 10 over n plus 3, and then 10 over n plus 2, and 10 over n plus 4. See if you're getting the same thing as me. Those back end terms in. We've got an nth partial sum here. And let's see if we can't make it go down. So in my first term, if I look at the second piece, where does he cancel?
Cancels the first and the third term.
Yeah, he cancels. So he's in the second position, right? He's in the second position in my first term. He cancels over here with the third term, first position. So it looks like a second position cancels, skip a term and go over one. And let's check. So my second term here should cancel to the right. Skip a term and go over one, and there it is. You see that? So this guy cancels to the right. The second term will cancel to the right. The second term will cancel to the right. So that means, let's see. All right, the second term. The second position, sorry, not the second term, but the second position. So that means this guy, who holds the second position, is going to cancel over here. And this guy, who holds the second position, is going to cancel over here. And this guy, who's in a second position, is going to cancel over here, which he does. But now, what about this guy right here? He's in a second position. For him to cancel,
It'll be the first of n plus 1.
it would be over here, but there's nothing over here to cancel, right? So he's going to be a leftover piece. He can't cancel because he would have to cancel over here. There's nothing to cancel with, so he's going to be left over. And same thing here. He's in a second position, right? So he is going to be left over because he has to cancel with something over here, and there's nothing to cancel with. So I know that my S sub n has to include, for sure, minus 10 over n plus 3 at the back end, and minus 10 over n plus 4 at the back end. Well, let's see about anything else. Oh, at the front end, what do we have? At the front end, what numbers do we have at the front end?
So 10 over n.
10 over 3. Now, why do we have up here 10 over 3 and 10 over 4 left over?
So it's going to play pre-second term.
Yeah, because remember, the second terms cancel to the right. The first terms, this is the first term, our first position. He's canceling to the left, right? First terms cancel to the left. And so if I'm looking at this 10 plus 4, he's a first term, and he would have to cancel over here, but he can't. Do you see? And 10 over 3 would have to cancel over here, and he can't. So 10 over 3 is left. 10 over 4 is left. Oh, what about these extras? Let's go back to the back end. He's in a first position. He's going to cancel this way. Well, so he'll cancel. This guy here is a first position. He's also canceling this way, so he's going to cancel over here. And so it looks to me that our nth partial sum is this. And this is what you'll box and on your homework. This is what you'll box and put in on WebWork and also on your test, right? You want all of those pieces together. Now, why are we doing this? Because a sum will converge if the sequence of partial sums converges. So now we're going to take a limit as n goes to infinity of this nth partial term. If the nth term in this sequence of partial sums, so the nth sum, the nth sum, nth partial sum. So what do you get when you take a limit as n goes to infinity of this? What's that equal? This guy goes where? This goes to 0. This guy goes to 0. The whole thing goes to what, Andrew?
7/12.
Yeah, it goes to 70 over 12, which we could reduce down to 30. Nope, 36. Nope, undo. 35 over 6. I think that's as far as we can go. So we would say that this sequence, or excuse me, oh my gosh, this series, which is an infinite summation, actually converges to 35 over 6. How are you guys, okay? Questions? Questions? You want to do one more practice?
Sure, this is going to sound really weird,
Yeah.
but this whole time I've been thinking of the fact that we got into recursion in computer science recently.
Did you really get into recursion? How cool! I'm telling you, series are really important to computer science. Series are really important for infinite, when you're studying infinite behavior. So physics, engineering, electrical engineering, actuarial sciences, when we talk about infinite behavior, series come up. Okay, series come up. And computer programming, right? This is how we program things with series. Okay, guys, so why don't you guys go ahead and I won't start geometric series. Oh, I know what I want to do. I'm going to do this. I'm going to add in, ready? I'm going to add in a saved photo because I accidentally closed it. There we go. Draw. Here's your practice. Here's your practice. Take 6 over 4n squared minus 1 and do the same thing we just did. Rewrite it as a partial fraction decomposition. Compute S sub n, the nth partial sum, and then find the limit as n goes to infinity. What did you get on top 2n minus 1?
A is 3.
Oh, yeah.
3 over 2n minus 1?
And then minus 3 over 2n.
Negative 3 over 2n plus 1.
Yeah.
James, are you getting that too?
I'm getting B is minus 3 and A is 3.
Uh-huh. And once you get that, then let's list out S sub n, right? What is S sub n? Let me wander and make sure everybody's getting